Now, what about another similar determination of the Gibbs free energy? But what if we aren't told explicitly our Gibbs free energy values? It turns out that we don't necessarily need to rely on Gibbs free energy. We can rely on the Gibbs equation to tell us the delta G is equal to the delta H of the reaction minus T delta S. And so if we know the delta H under starting state and the delta S under starting state conditions, standard state conditions, we can calculate those values. Again, from our table, we can see that we are given delta H's and delta S's, or S entropy values, and so we can calculate those in a similar fashion of what we did to determine whether a reaction was spontaneous. But rather than going all the way to entropy of the environment, we could just use this to calculate Gibbs free energy. So what does that look like? Well, we have to find out the delta H of the reaction. So using the information in our table, we can figure out the necessary values for the entropy and the enthalpy using the techniques that we developed over the past couple of days. So products minus reactants for the delta H's, we have the products, magnesium, enthalpy of formation of 0 because it's magnesium in the standard state, oxygen, so this is 0 for the products, minus the enthalpy of formation for the starting materials, the magnesium oxide, minus 601 joules, 0.8 kilojoules per mole, times 2 moles because there's 2 moles. This will leave an entropy of formation of positive delta H of reaction is equal to positive 1203.6 kilojoules, positive for the entropy of formation for the reaction. And then we can do the same thing for the entropy of reaction, but again, this one is less likely to be lots of zeros in it because entropies are typically non-zero. So again, products minus reactants, the magnesium, 2 times 32.5 joules per mole Kelvin for the magnesium, plus the oxygen, 205 joules per mole Kelvin for the oxygen. All products minus the reactants. In this case, the reactants were the magnesium oxide, has an entropy of 2 times 26.8, a positive value, positive value. Checking my math, 270 joules per mole Kelvin minus 216.4 joules per mole Kelvin for this reaction. So the delta H, so the delta H of reaction, the delta S of reaction, easily calculated, 1203.6 kilojoules for the delta H and about 216 joules for the delta S. But we care about whether or not the reaction is spontaneous, and so we combine these two in the Gibbs equation, delta H, 1203.6 kilojoules per mole, minus T, delta S, T in this case is 25 degrees or 298 Kelvin, times the entropy change. This entropy change, though, has to be in the correct units. 216.4 joules per mole Kelvin. We know that for every 1,000 joules, that is 1 kilojoule, gives us a value of 0.2164 kilojoules per mole Kelvin. So we do our multiplication, 298 times 0.2 gives about 65, 64.5 kilojoules per mole, and we subtract that from our positive value, so delta G becomes 1139.1 kilojoules per mole for the reaction, delta G of reaction. And it's very positive. 11. So this reaction very much does not progress this way. We'll talk about how the magnitude of delta G affects the extent of reaction shortly. But this reaction very much does not favor the products. So this reaction is not spontaneous under these conditions. So right now, determine delta G. And then from the sign of delta G, say whether it's spontaneous or not. Positive delta G, not spontaneous. Negative delta G, it is spontaneous.